Hey everyone, so our topic is all about geology and non-renewable mineral resources. So the intended learning outcomes of this topic are: discuss what are the Earth major geological processes and hazards, discuss how are the Earth recycled, discuss what are the mineral resources and what are the environmental effect of using them, discuss how long will supply of non-renewable mineral resources last, discuss how can we use mineral resources more sustainably. So let's move on to the question. What are the Earth's major geological processes and hazards? The Earth is a dynamic planet. Geology is a science devoted to the study of dynamic processes occurring on the Earth's surface and its interior. Three major concentric zones. The core is the Earth's innermost zone, extremely hot, with a solid inner part encircled a liquid core of molten or semi-solid material. Surrounding the core is a thick zone called the mantle solid rock, but under the rigid outermost part of the asthenosphere, a zone hot partly melted rock that flows. The Earth is a dynamic planet. The outermost and thinnest zone of Earth is the crust. Continental crust, which underlies the continent. Oceanic crust, which underlies the ocean basins and makes up 71% of Earth's crust. The combination of crust and the rigid outermost part of the mantle is called the lithosphere. So Earth crust and upper mantle major features. The Earth crust and upper mantle and dynamic layers that interact to shape our planet's surface. Understanding their features requires examining their composition, structure, and interactions. First is Earth crust. The Earth crust is the outermost solid shell of the Earth, relatively thin and compared to the other layers. Its thickness varies significantly. It can be over 80 kilometers thick in some places and less than 1 kilometer thick in others. The crust is divided into two main types. Oceanic crust. This is the thinner 5 to 10 kilometer and denser than continental crust, primarily composed of mafic rocks like basalt and gabbro. It's constantly being formed in mid-ocean ridges and recycled through subduction of convergent plates and boundaries. Oceanic crust is relatively young, generally less than 180 million years old. Continental crust. This is thicker 30 to 50 km up to 80 km in some areas, and less than the oceanic crust, predominantly composed of felsic rocks like granite, It's older and more chemically complex than oceanic crust. The crust is not a uniform layer. It's broken into several large and small tectonic plates that are constantly moving. These plates interact at their boundaries, leading to various geological phenomena like earthquakes, volcanoes, and mountain building. The second one is Earth upper mantle. The upper mantle lies directly beneath the crust and extends in depth of approximately 410 kilometers. It's divided into two main regions based on mechanical properties. So, lithosphere. This is the rigid outermost layer, encompassing both of the crust and the uppermost part of the mantle. It's relatively cool and brittle, making up to a tectonic plate. Asthenosphere. This is more ductile and less rigid layer beneath the lithosphere. It's hotter and more easily deformed than lithosphere, allowing the tectonic plates to move slowly over it. The asthenosphere is partially molten, contributing to the magma generation and volcanic activity. The upper mantle is primarily composed of peridotite rocks, which is olivine and pyroxene. The composition and properties of the upper mantle changes with depth due to increasing pressure and temperature. The transition zone is located between the upper and the lower mantle, approximately 410 to 660 km depth. Mark significantly changes in the mineral structure and the density. The Earth beneath it is moving. Convection cells or current move large volumes of rocks and heat is in loop within the mantle like gigantic conveyor belts. Flows of energy and heated material and this convection cells cause the lithosphere to break up into a dozen huge rigid plates called tectonic plates. Continents have split apart and joined as the tectonic plates drifted atop the Earth's atmosphere. The Earth beneath your feet is moving. The forces produced at the plate boundaries can cause earthquakes, eruption, volcanoes, and mountain erupting. The forces produced at these plates boundaries can cause earthquakes, erupting volcanoes, and mountains to form. Oceanic plates move apart from one another, allowing magma to flow between them. Much of the geologic activity to Earth's surface takes place to the boundaries between tectonic plates as they move in resulting cracks. Oceanic ridges may have peaks higher and canyons deeper than those found in Earth continents. The Earth beneath your feet is moving. The two oceanic plates collide. A trench ordinarily forms at the boundary between two plates. When an oceanic plate collides with a continental plate, the continental plate usually rides up over the denser oceanic plates and pushes it down into the mantle in processes called subduction. The area where the collision and subduction takes place is called subduction zone. Tectonic plates can also slide and grind past another along in fracture or fault. In the lithosphere, a type of boundary called a transform fault.
So next, the Earth's crust is made up of mosaic of huge rigid plates. So as you can see in the image depicts the theory of plate tectonics, illustrating how the Earth's crust is divided into large, rigid plates that move and interact. The diagram shows two plates converging at a subduction zone, where one plate slides beneath the other, sinking into the mantle. This process, driven by the convection currents in the Earth's mantle, is responsible for many geological phenomena, including earthquakes, volcanoes, and mountain building. Next, the Earth's major tectonic plates. So the image is a map of Earth's major tectonic plates. It shows the boundaries between these plates categorized as divergent or where plates move apart, convergent or where plates collide and transform or where plates slide past each other. The different colors represent the various tectonic plates, highlighting their relative sizes and positions across the globe. The next one is the San Andres Fault. So the image is an aerial view of the San Andres Fault, a major continental transform fault in California. The fault line is clearly visible as a long, linear feature running through the landscape, marked by a distinct break in the terrain. This fault is the boundary between the Pacific Plate and the North American Plate, and its movement is responsible for many earthquakes in the region. So next, volcanoes release molten rock from the Earth's interior. So, an active volcano occurs when magma reaches the Earth's surface through a central vent or a long crack called a fissure. Next, many volcanoes form along the boundaries of the Earth's tectonic plates when one plate slides under or moves away from another plate. Magma that reaches Earth's surface is called lava. Volcanic activity can release large chunks of lava rock, blowing hot ash, liquid lava, and gases into the environment. So next one, internal pressure in a volcano can cause lava, ash, and gases to be ejected. So the image illustrates volcanic eruption, showing how internal pressure builds up within a volcano. This pressure, caused by rising magma or molten rock and trapped gases, eventually overcomes the strength of the surrounding rock, leading to an eruption. The diagram depicts the ejection of lava, ash, and gases, along with other volcanic hazards like pyroclastic flows and landslides. The image also shows extinct volcanoes, highlighting the different stages of volcanic activity. So next, earthquakes are geological rock and roll events. So forces inside the Earth's mantle and near its surface push, deform, and stress rocks. The stress can cause the rocks to suddenly shift or break and produce a transform fault or fracture in the Earth's crust. When a fault forms or when there is abrupt movement on an existing fault, energy that has accumulated over time is released in the form of vibrations called seismic waves, causing an earthquake. So next, an earthquake has certain major features and effects. So the image illustrates the major features and effects of an earthquake. It shows the focus or the point of origin underground, the epicenter or the point on the surface directly above the focus, and the propagation of shock waves. Secondary effects depicted include landslides on hilly terrain, liquefaction causing building damage, and flooding in low-lying areas due to the ground displacement. The diagram also highlights the lateral movement of two adjoining plates along the fault line as the primary cause. So continuation on earthquakes are geological rock and roll events. So the severity of an earthquake is measured by the magnitude of its seismic waves. The magnitude is a measure of shaking caused by the earthquake, as indicated by the size of the seismic waves when they reach a seismograph. Scientists use the Richter scale, on which each unit has amplitude 10 times greater than the next smaller unit. So these are the one of the sample of the measure of Richter scale. So first is the insignificant or less than 4.0 on the Richter scale. Next, minor 4.0 to 4.9. Next, damaging 5.0 to 5.9. Destructive 6.0 to 6.9. Major 7.0 to 7.9. And last grade over 8.0.
Earthquakes are geological rock and roll events. One way to reduce the loss of life and property damage is to examine the records or the historical records and make geologic measurements to locate the active fault zone. The first thing to do is map the high-risk area and establish building codes that regulates the placement and design of the building in each area. And the next is the people evaluate the risk and factor it into their decision about where to live. And the next is engineers know how to make the buildings and structures that more on earthquake resistance. About the earthquake on the ocean floor that can cause huge wave or what we call tsunami. So let's talk about what is tsunami. Tsunami. What is tsunami, by the way? So according to the Google, a tsunami is a series of a large wave generated when part of the ocean floor suddenly rises up or drop. The most large tsunami are caused when the certain type of fault in the ocean floor move up or move down as a result of a large underwater earthquake, a landslide caused by such an earthquake, and in some cases, a volcanic eruption or what we call underwater volcanic eruption. So tsunami are often called the tidal wave. Tidal wave. Although they have nothing to do with these tides. Let's talk about how powerful the tsunami is and how tsunami affects the earth or the earth's surface that surround us. Okay. First is the tsunami. They can travel far across the ocean at the speed of a jet plane. Jet plane. So it was so very fast. And the next is in deep water, the waves are very far apart. Sometimes hundreds of kilometers, and their crests are not very high. As a tsunami approaches in a coast, it slows down, its wave press squeeze closer together, and their heights grow rapidly. And the exciting part is, or you can say, it's so amazing but so dangerous, okay? When it hits the coast as a series of towering walls. Yeah, like a towering walls. The towering walls of water that can level the buildings. So, it's all very big. Okay? This is what's so scary. So let's talk about how the earth rocks recycled. Recycled? I thought only garbage can be recycled, okay? But earth rocks too. Okay? So let's talk about the three major types of rocks. I think you have an idea what are they? So let's talk about the main topic. So a mineral is an element or inorganic compound that occurs naturally in the Earth's crust as a solid with a regular internal crystalline structure. And the next is a few minerals consist of single elements such as gold, silver, and diamond, including the carbon. So the next is the most of more than 2,000 identified minerals occurs as inorganic compounds formed by various combination of elements such as salt or what we call the combination of sodium chloride or NaCl and quartzite or the silicon dioxide. And let's talk about the main topic, the three major types of rocks. So, but before that, let's talk about what is rock. Rock and roll. No. By the way, back to topic. So, rock is a solid combination of one or more minerals found in the Earth's crust. Okay, rock. Some kinds of rock, such as limestone and quartzite, contains only one mineral, while most consist of two more minerals such as granite and a mixture of mica, feldspar, and quartz crystals. Here's the three types of rocks. The first is the sedimentary rock, or what we call the sandstone and limestone. The next is the igneous rock, or what we call granite. that we can found in the buildings or in our home, the design. And the last is the metamorphic rock, or what we call the slate and marbles.
Have you ever wondered how rocks on Earth transform over time? Rocks might seem permanent, but they are actually part of an extraordinary processes that reshapes them over millions of years. This is called the rock cycle, a natural interaction of physical and chemical processes that slowly recycles Earth's rocks and changes them from one form to another. Earth's rocks are recycled very slowly. The rock cycle is the interaction of physical and chemical processes that change rock from one form to another. It takes millions of years for this cycle to happen. What are the mineral resources and what are the effects of using them? Non-renewable mineral resources include metals like gold, silver, iron, and aluminum, non-metals like limestone, sands, and clay, and fossil fuels like coal, oil, and natural gas. These are finite and take millions of years to form. The use of mineral resources brings significant benefits but also possesses serious challenges. Minerals are essential for economic growth, technological advancements, and infrastructure development, supporting industries and improving modern life. However, their extraction and use often lead to environmental degradation, including habitat destruction, pollution of air and water, and resource depletion. These activities can also cause health problems for workers and nearby communities while contributing to social conflicts over land use and resource distribution. Balancing these benefits with sustainable practices is crucial to minimizing the negative impacts and ensuring long-term availability. Each metal resource that we use has a life cycle, starting from mining, metal ore, separation of ore from waste material, smelting, melting metal, conversion to product, discarding of product, and recycling. This cycle emphasizes the importance of recycling to conserve natural resources and minimize environmental impact. So these are the several ways to remove mineral deposits. Shallow mineral deposits are removed by surface mining by removing vegetation, removing the overburden or soil and rock overlying a useful mineral deposit, placing waste material set aside in piles called spoils, and open pit mining. Strip mining is useful and economical for extracting mineral deposits that lie in large horizontal beds close to the Earth's surface. Area strip mining is used where the terrain is fairly flat. A gigantic earth mover strips away the overburden and a power shovel removes the mineral deposit. Controlled strip mining is used mostly to mine coal on hilly or mountainous terrain.
So next, continuation on several ways to remove mineral deposits. So first, mountain top removal uses explosives, large power shovels, and huge machines called drag lines to remove the top of a mountain and expose seams of gold. Next, subsurface mining removes mineral from underground through tunnels and shafts. So the image illustrates the harmful effects of extraction, processing, and use of non-renewable mineral or energy resources. So next, the image is illustrating the types of mining. First is the open pit, second strip, contour strip, and mountain top removal. So let's move on to the next slide, which is mining has harmful environmental effects. So scarring or disruption of the land surface, mountain top removal destroys forest, buries mountain streams, and increases flood hazards. Wastewater and toxic sludge produced when the coal is processed are often stored behind dams in these valleys, which can overflow or collapse and release toxic substances such as arsenic and mercury. Surface mining in tropical forest and other tropical areas destroys or degrades vital biodiversity when forests are cleared and rivers are polluted with mining waste. Produces toxic waste materials such as lead dust, which can cause lead poisoning and irreversible brain damage in children. So, continuation, subsurface mining disturbs less land than surface mining disturbs, and it usually produces less waste material. Next, creates hazards such as caves-ins, explosion, and fires. Miners often get diseases such as black lung, caused by prolonged inhalation of coal dust in subsurface mines. Causes subsidence, the collapse of land above some underground mines. Let's move on to the next slides, which is removing metals from ores has harmful environmental effects. So, ore mining typically has two components. Ore mineral containing the desired metal. Waste material. Removing the waste material from ores produces waste piles called tailings. Heating ores to release metals is called smelting. Without effective pollution control equipment, smelters emit enormous quantities of air pollutants, including sulfur dioxide and suspended particles. Chemical can be used to remove metals from their ores. So, how long will supplies of non-renewable mineral resources last? So, next slide, mineral resources are distributed unevenly. So, the Earth's crust contains fairly abundant deposits of iron and aluminum. Manganese, chromium, cobalt, and platinum are relatively scarce. The Earth's geologic processes have not distributed deposits of non-renewable mineral resources evenly among countries. So next one, supplies of non-renewable mineral resources can be economically depleted. So the future supply of non-renewable minerals depends on two factors. So the first one, the actual or potential supply of the mineral, the rate at which we use it. So minerals may become economically depleted when it costs more than it is worth to find, extract, transport, and process the remaining deposits. Option when these occurs are first, recycle or reuse existing supplies, waste less or use less. Next, find a substitute or do without. Next one, market prices affect supplies of non-renewable minerals. So geologic processes determine the quantity and location of a mineral resource. Economics determines what part of the known supply is extracted and used. An increase in the price of a scarce mineral resource can lead to increased supplies and encourage more efficient use. Next, standard economic theory may not apply because most well-developed countries often use subsidies, taxes, regulations, and import tariffs to control the supply, demand, and price of minerals. Most mineral prices are kept artificially low. Next is mining lower grade ores the answer. So, extraction of lower grades of ore is possible due to new earth-moving equipment, improved techniques for removing impurities from ores, and other technological advances in mineral extraction and processing. Mining low-grade ores is limited by increased cost of mining and processing larger volumes of ores. So next one is mining lower grade ores the answer. So mining lower grade ores is part of the answer to increase mineral extraction, but it's not a complete solution on its own. It presents significant challenges in terms of energy consumption, environmental impact, and economic viability. While technological advancements are making it more feasible, other strategies like recycling and developing alternative materials are also crucial. So, increased shortage of the fresh water which is needed to mine and process some minerals, especially in arid and semi-arid areas. Environmental impacts of the increased land disruption, waste material, and pollution produced during mining and process. And last one, can use microorganisms that can break down rock material and extract minerals in a process called in place or in situ mining or biomining. So next, can we get more of our minerals from the oceans? The answer is yes, because some ocean mineral resources are dissolved in seawater. Next, low concentrations take more energy and money than they are worth. Hydrothermal ore deposits are rich in minerals such as copper, lead, zinc, silver, gold, and some of the rare earth metals. Next, glowing interest in deep sea mining. And last one, manganese nodules cover large areas of ocean floor.
How can we use mineral resources more sustainably? So we can find substitute for some scarce mineral resources. Human ingenuity will find substitutes. Current materials revolution in which silicon and other new materials, particularly ceramics and plastics, are being used as replacement of metals. Finding substitutes for scarce minerals through nanotechnology. We can recycle and reuse valuable metals. A more sustainable way to use non-renewable mineral resources, especially valuable or scarce metals such as gold, copper, and aluminum, is to recycle or reuse them. Recycling has much lower environmental impact than mining and processing ores. Cleaning up and reusing items instead of melting and processing them has an even lower environmental impact. So we can use mineral sources more sustainably. So instead of asking how we can increase supplies of non-renewable minerals, we should be asking how can we decrease our use and waste of such as resources. Since 1990, a growing number of companies have adopted pollution and waste prevention programs that have led to cleaner production. There are three big ideas. Dynamic forces that move matter within the earth and on its surface, recycle the earth's rocks, form deposits of mineral resources, and cause volcanic eruptions, earthquake, and tsunamis. The available supply of mineral resources depends on how much of it is in the earth's crust, how fast we can use it, is a market prices, and the harmful environmental effects of removing and using it. We can use mineral resources more sustainably by trying to find substitutes for scarce resources, reducing resource waste, and reusing and recycling non-renewable mineral.